left it on and closed this time. Sorry for this. Um, cool. So I was here. Exactly. So you have that, and so you're gonna have basically P uh, conjugate times P, which I think that is just one, isn't it? Uh, plus P conjugate times Q plus Q times P plus Q conjugate times Q conjugate. I think, sorry, times Q. So I think that these things are basically one, right? Where's the mouse? Where's the mouse? Because basically it's the same function. So I think that it's, I'd want to check that. Let me see. So wave function times its conjugate. Its conjugate. I think it's one, right? Yeah, it's one, right? Because it's the same, like, yeah, it's one. It's one because it actually gives you the, like everything that is exponential, everything that is complex will just kind of minus out to the power of zero, right? So I think that is function modulus complex conjugate. I mean, it's probably not always the case, but I think it is the case by for these. For yeah, yeah, okay, exactly. No, intensity, identity. No, okay, sorry. I don't know. Uh, uh, because I think that it's in this case because it's normalized, right? I think that the so what that would give you, right, is would give you sort of the, it's like the inner product, so it would give you the sort of the overlap, right? And so like that's kind of okay. It's not the same, so I'm not so sure. I think it should give either one or I don't know, or zero because they don't have an overlap with the. Hmm. I mean, it's kind of these times its own conjugate, like I don't know. And then I guess what I'm saying is it should be one, to be honest. Because so my intuition tells me that now here we kind of have to deal with these terms, right? And so because what is the information that we have? We say that the regions are not overlapping. So my assumption is this means that the product, the inner product of these two-way functions should be zero. But I don't know if it's the inner product or the inner product, sort of the product with its own, with the complex conjugate, right? Um, overlap of wave functions. Overlap wave functions. I'm gonna go ahead. I think maybe I shouldn't just search too much about it, but then overlap. Calculate overlap of wave functions. Calculate. Because I still have trouble and sort of with the interpretation of like why I would multiply by the complex conjugate in this case, right? Uh, Okay, look at this. Maybe we'll get it from this picture. How do we know that that would be, yeah, okay, so here's like times, right? So it's difficult to find. Another way to look at it is the amplitude squared of the real wave, blah blah blah. So I don't know how to look for this. Calculate wave function overlap. This seems to be the right question. How do I? Maybe overlap is the wrong way of phrasing it. Because I'd go ahead and I'd say that, right? Because I think what it means is basically that these two things are like, this is zero, right? So I think this is zero. That would be my assumption, okay? So maybe we'll just take a look at the solution. This will be zero. My assumptions is that these things will just be one. It's an assumption, I don't know, right? So there's definitely time, it's definitely not time dependent. And then so we have to calculate this thing here, right? P and Q. So this means this is P, this is Q, right? So essentially you have this time component that gets multiplied and squared, and then you have these times these. But these things are time independent, right? These things are time independent just by definition. So I think, yeah, this would be time independent. I don't know. There's something off with these that I'm not super happy with. Oh well, and actually I still have to square that actually. Oh, no, that's correct. That's like these, and then the modulus out of that I have to take. But these things are basically, oh God, I don't know because I don't know because I don't know. Let's take, okay. So I shouldn't. I didn't want to do this. And probably it's the first problem. I should probably do this anyway. But my assumption is these, and then I'd say this times this is time independent. What does it say? So if the regions don't overlap, we have that this times this equals zero. That makes sense. And so we say that what? Okay. So everywhere there, therefore. Okay. I was not far from that though. I'm kind of missing the. I don't know if I did correctly with these things here, right? I guess these things like kind of cancel each other out because of what I just did, like the t components, right? But still, that is awkward though, because unless. Okay, yeah, okay. Unless now in hindsight it makes sense. That is not one, so that was the wrong thing. So this is zero as well, right? Because it's also the overlap. Yeah, maybe. Oh no, of course, because this thing. Yeah. So these two things are zero. I think that was the right assumption to make. And then and then you kind of basically have this, which is basically this square and this square, right? Okay, but in a way that is like these things don't disappear, right? In this case. So why is that not time dependent? Which is time independent. Because now we have the next one, which is basically assume that the two regions overlap partially. And so starting with the initial wave function, show that the probability density is a periodic function of time. And so now we have to have a time component, but I don't know how to do this at all because basically, um, mm, 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 mm. Because basically, okay, now I just say, of course, that's not zero anymore. So we're back at this point, right? But we have these two components here which are not zero, right? So we need to calculate P transpose, so this transpose times itself. And this is what, like, how does time dependence come here? I don't know. Hmm. Unless, of course, does come, right? Because so here, these two components, I forgot what I said, is in this case, they cancel out. That's why you just are left with d squared. With this squared, sorry. Here they also cancel out because it's one of them is going to have the opposite sign of the other, right? So they cancel out. And this one's a zero. So you have a time independent thing. Now, when these two things are not zero, we have, let's kind of clear that out again, and let's have, we have P transpose times P. So we know this is actually, in this case, just psi 1x squared because the exponential terms cancel out. Then we have the same, this is what we had before, right? So, and these are time independent terms. But now we have basically so now we have like P transpose times Q plus P times Q transpose, right? But I mean, in this case, these things don't cancel because they have maybe different energies associated to it, right? Remember, these I think will have the E1 and this will have the E2, so they'll have two different Hamiltonians attached to it. Here they cancel because it's the same term, so it's P times P transpose, and so it's the same Hamiltonian or the same energy, and so they'll cancel out. But here they won't cancel out, right? And we know there's an overlap, and so we're going to have for each of these terms, and let's just now zoom into one of the terms. So we will have basically, the E, and then we'll have the, so what was that? So that was like minus I E T divided by the Planck constant and square root of 2. So that's kind of the component of, say, psi 1x, kind of transpose. And so that's like a plus because we just changed the sign of the complex part times, and now we get like e to the power of minus I, but this e is different, right? So I think it's e sub 2 and is e sub 1 times t, Planck constant, blah, blah, blah. So they don't cancel out, times psi 2, right? And so they don't cancel out. But we can forget these two parts are time independent, and then here we have time dependent. So now we just have to focus on these two things. I just know they are, they are cyclical because it's an e to the complex power, and I know that kind of thing spins around. And I yesterday or 2 days ago I was taking a look at e to the complex power definition, and there's a definition in terms of sine and cosine, which I think would just directly answer the question, right? Complex power for complex number, no. E to the power of a complex number. Yeah. So that does. There is, it's a sine plus cosine. Yeah, there you go. It's cosine plus I times the sinus. So yeah, so and that, I think that is enough to answer the question, right? Because, well, we know these components have that kind of thing. Let's see how the actual answer looks like if I manage to get back here. At this point, I'm just curious to see that. I don't want to spoil D. Okay, so we have, oh, not exactly. If the two regions overlap, the probability density will be, okay, that's what I calculated before, plus, and here is the overlap. Okay, I'd have to calculate that out. I don't know what these things are, though, where we have set psi 1, 2. Oh. So that's the psi of the intersection. And what is these theta thing here? WT? What the? Maybe does it have to do with like the free particle thing? Wave function free particle, because that's like angular momentum or something like that, isn't it? Or I don't know. There's something associated to it. Yeah, there you go. You see? There you have the WT thing. Okay, so that's where it comes from. Um, I'm not so sure I got it right though, because there's just a cosine here. That's not what I was expecting, to be honest. I'll just have to run the math and see if I can get that. Plus, plus. And the half is missing here as well. I think I just have to run them. I have to do that. I won't have time now, but I'll do that in the next session. I'll have to run the math. I think that is, yeah, because essentially you've got like, it's the cosine of all this kind of stuff. So I just have to E1. Okay, so actually I think I can get there because it's E1 and E2, and that's E1 minus E2, right? So if I try to reverse engineer these, I guess that's what they've done. So what they've done is they've set E1 minus E2 to like Planck constant times angular momentum, or W, whatever that is. That is why they get like a much cleaner expression. Okay, but I'll do that. So I promise I'll do that. And let's tackle D. And I think that we'll call it a session. Again, as a short sprint, but whatever. At least we're moving forward, starting with the same initial wave function. And assuming that the two eigenfunctions are real and isotropic, take the two partially overlapping regions to be two concentric spheres of rarity, R1 or 2. Okay, so this is going to require a bit of digging. So what is the probability current that flows through probability current? This is something I don't know. So the probability current is a mathematical quantity describing the flow of probability. Specifically, if one thinks of probability as a heterogeneous fluid, then the probability current is the rate of flow. So we have a rate of something, a rate of flow of this fluid. Is that the sort of the derivative, maybe, of the probability? Is the rate of flow So it is a real, no, it's a vector. It's a real vector that changes with space and time. Probability currents are analogous to mass currents in hydrodynamics. Probability current is related to the probability density function via a continuity equation. So what is the formula? Let's some examples. Particle in the box. So for a particle in the box in one spatial dimension of length L confined in the region between 0 and L, the energy eigenstates are these, and 0 elsewhere. The associated probability currents are, oh god. Okay, so there's, it's, so, what? So it's the derivative with respect to x. So there is definitely some partial, like some rates involved in there. Okay, so I guess this is in a way somehow associated to like the change in regions, right? And then you do it, the how does the probability change for a plane wave propagating in space? The probability density is constant everywhere. Okay, so you have a probability density that is constant everywhere. So the rate of change is 0. This means over time, the probability density, okay, so that's how the probability density changes in time. So the probability, but the probability current is non-zero. Okay. The square of the absolute amplitude of the wave, the square of the absolute amplitude of the wave times the particle's speed. Illustrating that the particle may be in motion even if its partial spatial probability density has no explicit time dependence. Oof. So this is then something that relates the probability with the actual wave function in a way. So maybe this is something like the rate of change of the probability density with respect to the actual wave function or something like that. Like I don't even know what flow probability flux. The rate of flow. We don't know what flow is though. Probability currents. Then the probability current is the rate of flow of this fluid. So the probability currents are analogous to mass currents. Mass transfer bulk flow is the movement of fluids down a pressure or temperature gradient, particularly in life sciences, studying about the fluid. Okay, I don't know exactly. I think I'm getting an idea, but I don't know. Gotta switch back to another thing now, but at least I think I've got one almost covered. I think I've got one almost completely covered. Yeah, I think so. It's just like I just have to verify that I got the maths right for these, for the C, but I think I have. And then D is just it's just complicated. But I think I've gotten the. I just have to check that I've gotten the maths right and that things check out here. But I think that is more or less right. Yeah. Cool. See you next time.